And Volker, thank you so much for accepting our invitation. And now the floor is yours. Thank you.
Thank you, Omnia. Yeah, well, thank you for inviting me to this. I'm very honored to be here and talk about this. Here, the title is about the role of voice recognition in human communication with language. So it's not specifically about forensics, but it is more about really the integration between voice recognition and language. I hope you find that interesting. I'm happy to extend the discussion on forensic topics, of course, as well. And I'm sure this is also fundamental knowledge that is relevant for forensic purposes as well. Okay, so the role of voice recognition in human communication with language. First of all, I guess most of you are aware of that. What is voice recognition actually? Well, phenomenon. We hear a voice and we can recognize a person by their voice.
Tell them, don't double my rate. You don't double my rate. You should call them, you should email them, write on their Facebook page, tweet them.
Okay, there was one hand going up. I think it's probably a little bit of an unfair experiment because most of you maybe don't know that voice in the original. But the person who raised the hand, I think, yeah, we don't have a chat. But anyone wants to say who it was? Anyone has a guess?
Was it Barack Obama?
Absolutely, it was Barack Obama. I thought I'd choose someone whose voice is pretty, maybe one of the voices that is very well known around the globe. Very good voice recognition. But basically, so if I play this example to groups that are more familiarized with the original voice of Barack Obama, usually after the first syllable, the first hands go up and people say that, oh, I know who this is. Yeah, so because he has a very characteristic voice, he is well recognizable. And the example basically tells us that next to a linguistic message, the speech signal contains numerous speaker-specific detail, and we call that speaker-specific detail also indexical detail or indexical information. And we can characterize and recognize speakers based on that indexical information. So one of you recognized the voice now, but others probably, when you hear that voice, you might not recognize the original speaker, but you can characterize the voice. You will probably hear immediately, oh, that's a male speaker. You can probably estimate the age of the speaker, and so on and so forth. There's all sorts of information that the voice carries. So when we identify or in voice recognition tasks, in a nutshell, there are basically two different tasks that are essential that we can probably reduce most of the voice recognition task to. And one of these tasks is identification, and the other one is discrimination. And identification is basically the task by which we identify an individual based on knowledge previously acquired by the speaker. So basically that means we need a model of the speaker. We need to have been familiarized with the speaker to later re-recognize or identify the speaker, we say. Discrimination is basically the act of comparing different voice pairs to decide whether the samples stem from the same or different speakers. So for discrimination, you don't need to know the speakers. You just hear two different voices and you say, oh, they are from the same speaker or they are from different speakers. And I would say that, well, there are countless variants of these two tasks, but I guess not all my colleagues would agree with that. But I think if we sort of push them here and there a little bit, we can always lead them back or reduce them. They can be broken down to these base tasks of identification or discrimination. If you think of processes, I don't know how familiar you are with voice recognition in technical circumstances, for example. If you think of speaker diarization, for example, yeah, that's the process of when you have a dialogue of different speakers and you want to know who is speaking at what time. Well, to some degree, that is recognition you're carrying out because you need to know the voice, but you're also doing discrimination because you're comparing speakers against each other. So I'm saying when you're breaking things down, you can probably break it down to these two base tasks. And important in here is that the result is always a probability or a likelihood. So we're talking about what's the likelihood that a speaker is, that a voice sample is from that speaker population, for example. And now I think I have to get up for a second. So our shutters, they always automatically shut down, and every 20 minutes or half an hour, I have to stop them from doing that. Otherwise, I'm going to sit here in the dark. Okay, sorry for that. Okay, so important is really that the results is always a probability or a likelihood. Very often I'm approached and asked by, in particular in forensic circumstances, and people ask like, oh, voice recognition, can it be done, yes or no? And obviously we can never answer such a question with yes or no. We can always say, well, yes, but with a certain probability. Yeah, so we can always recognize, but maybe the probability that we are correct drifts towards zero, or in other circumstances it may drift towards one. And of course there is a huge bandwidth in what's the probability that we are correct. Okay, so the identity recognition in voice, I also want to make you aware of here in these few introductory slides. The identity recognition in voice is very complex, and it consists of many factors that need to be considered when we are talking about a recognition process. So if it's about human voice recognition, so the ability of a human to recognize a voice, I would say that the pre-voice exposure phase is the phase where voice recognition starts. Then we are talking about a voice exposure phase, and we also have a post-voice exposure phase. And in the pre-voice exposure phase, there is context that matters and expectation that matters. So context basically raises expectations about voices to occur, and your expectations then matter. It's hard to recognize a speaker when you do not expect that person under certain circumstances. No? So you really have to have a base expectation for this to happen. Then when we get into the voice exposure phase, or right at the beginning of the voice exposure phase, the attention matters tremendously. So if you're not paying attention to the voice during the exposure phase, you will probably not recognize. So your perceptual mechanisms need to be active or need to be aware of, oh, that they want to identify a person also in a certain circumstance. And many experiments show that this is not naturally always the case. So if you, for example, or there is there are paradigms of experiments showing that when, like, let's say you call a call center and the person disappears for a minute or two, and then another voice comes on, most people actually don't realize that the voice in the call center changed it, because it's not really relevant for you. You're not paying attention to this. You're not expecting that particular change to happen because you expect the same person to come back. So this is basically a situation where the attention to the voice is very low. I pointed out a link to a YouTube video that's also a nice example to that gorilla experiment, showing you an attention mechanism. It's this gorilla appearing. Maybe most of you probably know that experiment is a gorilla. You're trying to count people passing a ball to each other, and then all of it, like, and you have to count who passes the ball to whom, or how many times the ball is passed. And then at some point, a gorilla walks through the scene, and most people don't even notice that there is a gorilla because they are busy with counting the balls. And similar situations might occur in voice recognition, that sometimes, like if we're just paying attention to other things and not to the voices, then that matters tremendously, whether we have a recognition success or not. And then, of course, once we are in the voice exposure phase, the channel matters, signal quality, background noise, duration, are there competing speakers in the sample, and so on and so forth. And for during the voice exposure exposure phase, also your training experience matters with that particular voice. So this is absolutely crucial, whether you know the voice well or not well. So you're within speaker, are you familiar with the within speaker variability of that particular voice? Do you know that voice under different conditions? That is tremendously important for recognizing the voice under highly variable conditions in particular. And you're better also maybe at recognizing some voices than others. It's just some voices might have more recognizable properties than others. Then the speaker matters. Speakers might have an interest in being recognized or not, and probably they adapt their voice signal, their vocalization to whether that interest in recognition is there, so they adapt the signal to a voice that makes them more recognizable in one situation than maybe in another situation. And then in the post-voice phase, then the recognition actually of the voice, that is then immediately also training for the next voice, for your next voice recognition or your next voice exposure by that particular voice. And we're looking at voices in voice recognition in dialogue situations later, and we will see that all these details are going to come up there. So this indexical information, where did that actually that idea come from? So this is a very brief history of indexical information in speech, and it probably came from Charles Peirce's semiotic theory that was built around the 1860s. And Charles Peirce defined an index as a sign that has a real relation to the object. So for example, smoke is an index of a fire, but that also means that relationship is totally non-intentional. So the fire doesn't send the smoke to be recognized as a fire. So there's an absolute non-intentional relationship behind this. And that idea was basically carried over into phonetics. My impression is that it's mainly due to David Abercrombie, who introduced the term in his introduction to phonetics to refer to speaker-specific information in the speech signal that is non-intentional, but aids listeners recognizing who is speaking, for example. And that made indexical information traditionally be seen as unwanted information in the signal, more like the noise, in particular when you're dealing with the linguistic content of the signal. So that is basically something we got to get rid of. It's an uncontrolled byproduct of the speaker. So speakers involuntarily give it away, like the example with the smoke and the fire. So the fire doesn't intend the smoke for any communicative purposes. So speakers don't want to communicate with this. They just basically accidentally give their indexical information away. It's also been seen then as being static over time. So over the course of an utterance or a discourse, it's basically features that are around this or sort of in the speaker's speech that are omnipresent and that are omnipresent and static over time. So they are rather given something, they're not acquired, they're rather given, and people often argue mainly by anatomy. So it's basically our vocal tract configurations, larynx, and everything that contributes to our voices being idiosyncratic, individual, and carry these indexical pieces of information. And that's probably true in many domains when we look at this static over time approach, or how many domains view or model speaker-specific features. So in automatic recognition, maybe some of you will know that, like X vectors or embeddings for speaker embeddings, they reduce entirely highest speaker characteristics, for example, to a 512-dimensional vector. So it doesn't matter at what point in time the information occurs. That's basically a characterization of the speaker as such. And to some degree, that makes sense. And for some applications, that makes great sense, of course. But I'm trying to convince you today that probably recognizable features are much more than this static information. So typical reasons for studying voice recognition in the past were, well, in phonetics and psychology in particular, academic interest, that we're interested in understanding the process with which how recognize each other. So with which we can recognize each other, with which humans can recognize each other by their voice. The sentence should be. Sorry, that had a little accident. So we're interested, in understanding these processes. There is an academic interest in there, and that leads to a lot of applications. Voice recognition offers many practical applications. For example, as we mentioned before, in forensic voice analysis, speaker comparisons or voice parades, or in speaker verification for access systems like access to online banking via voice. Some of you might have registered to banking systems where you need to say sentences like "my voice is my passport," then your model is stored, and when you want to re-enter the system, then it recognizes you by your voice over the phone, for example. And or speaker diarization systems for automatic discussion processing that have a lot of applications once they work. Okay, and in some of these applications, also here in Zurich, we are working. We have a particular focus on. These are in particular these forensic voice analysis application. We have a center here, as Omnia mentioned in the beginning, that is mostly for research and education, the Center for Forensic Phonetics and Acoustics. You find more information under that link if you're interested in all sorts of projects we are carrying out in there. And then many of us here in Zurich are also involved in a company, JP French, that was originally founded by Peter French, who I have 2 decades of collaborations with. By now, he's also involved in the center in Zurich, and he's originally set up that company, and many of us in Zurich are now co-working with the company, JP French, on practical casework and trying to implement that these research aspects in particular into casework. So you find more information on these pages. But this is not really where I want to take you to in this talk. In this talk, really, I want to pose the question more, well, why has evolution actually equipped us, or why has evolution equipped us with voice recognition skills, but not, for example, with hand or foot recognition? So we're good at recognizing each other at some features, for example, voice, for example, also faces, we're very good at. We're really bad at, and there's a lot of evidence for that, we're really bad at recognizing each other by our hands. Probably our hands contain equally recognizable amount of detail as our faces, but cognitively, our cognitive mechanisms have never been tuned to actually recognize hands. Our hands, for example, contain fingerprints. We are super, super bad at recognizing fingerprints, even though technically that works perfectly fine, or with a high reliability, we can recognize individuals by their fingerprints. But this is something that evolution has not equipped our cognitive mechanisms with, that we can do that. So today I want to introduce you to voice recognition as a process that is deeply integrated into human communication per se, and in particular into human communication with language. And I want to argue that this is probably one of the reasons why voice recognition became such an important skill for humans. So it's not just that we can recognize a voice that is round the corner speaking, or like someone phones us without an identity on the phone before, and we can recognize that voice. This is voice communication, voice recognition. I want to convince you about this today is really a process that is essential for all sorts of dialogue communication that we do on an everyday basis, and that is maybe the reason why it became such an important skill for us. And as such, I also want to challenge the traditional view of voices as a static information in the speech signal, because to be able to actually use voice communication for communicative purposes, well, we also need to be able to have identity varying across speech signals, and that's a process that I like to refer to as indexical dynamics, so that some parts of our speech might be more recognizable than others, and also that we are able to modulate that recognizability so that we have some sort of decision capability of saying at what point we want to be recognizable, at what point we want to be not recognizable, or we don't need to be recognizable, and which would basically mean that identity is not a static property of a speaker. And then, yes, I want to make you think about that. Listeners rely on recognizability for communicative purposes and use this indexical dynamics and this non-staticness of recognizability actually in communication. And then it's a little bit in brackets, it's a side note, but also important. I find hardly any of these processes are probably explicit, yeah? Because if they were explicit, we would have been, or we would be aware of them much more. It's probably all sorts of processes that we implicitly carry out on a daily basis. We'll look into details now. Okay, if at any point there are questions already, understanding questions or something that you missed or so, please just jump in with your saying something. This can be a bit interactive, I guess. So voices are essential in communicative situations, and I want to give you an example for that, what I mean with this, why are voices important in communication. Well, this is an example from German. It might be challenging for many of you to understand this, but hopefully you can get my point with this. Let me play the example here first.
Aber jetzt war ja wohl Herr Eichel, war ja wohl die rot-grüne Regierung der Europäischen Union. Ich glaube, dass man auch mal fragen muss, wie weit geht denn eigentlich?
Yeah, so even if you don't understand the content, you will have heard, well, this is well, it's a sort of I'm not sure it's typical, but definitely frequent discussion, type of discussion, political discussion that you might come across on the German television when there is a talk show and politicians are invited, and at some point they really disagree about things and everyone just speaks in and wants to make their point and wants to get hold of the dialogue. And if there weren't any different voices, we wouldn't be able to follow any of this. Imagine each of these speakers spoke with the exact same voice. Yeah? So we wouldn't be able to attribute any of those contents that we hear to any of the speakers. I'm not saying that we can readily understand everything that they are saying if they're just talking wildly for each other, but having different voices in there, of course, is essential to structure that dialogue. And I think actually I've said, yeah, so having different voices is fundamental for structuring that dialogue. And coherent linguistic processing is only facilitated when the voices can be distinguished, and partly also when they can be recognized. So if you know some of these politicians by voice, you just hear that the person is speaking, and you immediately know how to interpret that particular utterance that they are actually
This video, presented
saying.
by Saimu Zhang, explores human-AI collaborative writing processes and outcome to tap into the affordances and constraints of language models.
I think that is something. Oh, now it's gone. Okay, so I thought it came from my slides, but it came from somewhere else. I think so. Yeah, so imagine all speakers had the same voice. It would be pretty impossible to follow any of this dialogue. So the first question that we need to ask here is then, how can identity vary across speech at all? How can an utterance be more identifiable at some points and less at other points? And how can speakers in general maybe make themselves more recognizable in some situations compared to others, or in general? And one example I want to bring here is a way in which we can probably maximize our anatomical vocal tract detail in the acoustic signal. So when you think of speech production, you can think of the vocal tract as maybe an equivalent to our outside face, that we have a face inside. So I like to call it the vocal face, basically, our vocal tract properties. Here you see a sagittal cut through a human head from an MRI image, and you see like these white points sort of highlight the outline of the vocal tract, and we see all sorts of detail from the pharynx and the oral cavity. And of course, this is only one cut through the person. This is a three-dimensional space we have to imagine, and at every cut that we did along the vertical dimension, we would get a lot of detail from that vocal tract. And the vocal tract, basically, the way it works, so if we think of a face, then basically we have light rays hitting the face, and then they reflect from the face and arrive at our eyes, and interpreting these light rays basically lets us interpret the facial individualities. And how does it work with the vocal face? Basically, we need a source signal. We need to do this via acoustics. So we have a source signal in the larynx that we build. We send it through the vocal tract, and in the vocal tract, it gets shaped, that is characterized by the so-called vocal tract transfer function. And this process you might have come across before also as the source filter process. So we have a source signal that is then filtered in a variety of cavities in the vocal tract, and then leads to an output signal that we call speech. So for that vocal face to become maximally identifiable, it is essential then that that vocal tract detail here in the middle. Can you actually see my mouse when I'm showing something with the mouse? Okay, yeah, I see Omnia's nodding. No, so it's got, yeah. So to, oops, now so for the vocal face to be maximally identified, is essential that that vocal tract detail here is rich. So this vocal tract transfer function should be sampled in as much detail as possible. And here's an idea of how we can do that. Basically, one way of doing this would be, instead of speaking with a steady state voice where I'm not changing my harmonics, so saying something like ah, instead of with a steady state voice, I'm sweeping my harmonics through the vocal tract by doing something like ah, ah, ah. Yeah? And by sweeping the harmonics through the vocal tract, that's what you see here on the right. You can see that, so the harmonics run up and down, and they basically sample all the details of that vocal tract transfer function while they are doing that. So that is one constellation of which I'm thinking of that might provide a very rich information about the speaker while keeping the voice rather steady state, keeping vowels rather steady state, without modifying the intonation much. It would keep the detail actually poorer. So hypothesis leading from this is speakers are better recognizable for sweeping as compared to when producing steady state vowels. And this we actually tested in an experiment where we used utterances produced produced by 15 speakers as training material, and then had the same speakers producing test material as steady state and so-called contour vowels. So they produced low, mid, and high-pitched vowels. We asked them to do something like and then a falling contour, and a fall rise, and a rise, I actually have an example there, but I did it now myself, so it's a sound example, so you heard it yourself. Produced by me, but that was basically the idea behind it. We to make it a little bit more realistic, when the speakers came in, we told them, oh, those are the 6 tones of Mandarin and you're going to learn it. And we had a Mandarin instructor teaching them those tones, but not telling them, of course, Mandarin actually only has 4 tones. There are no 6 tones. There's not the 3 level tones are not existent, but we just wanted to make the experiment a little bit more real. And then for testing purposes, then we trimmed the material so that from each vowel we had the exact same duration, had a little fade in, fade out. That's what you can see on the bottom in that graph, so that not one of the, like the fall and fall rise would typically be slightly longer than the steady state vowels. So we always took the center where most of the movement was, and then use that for the testing purposes. Now we put that in a recognition experiment first with computers, and with the computers we trained them on the 15 voices with, I think, 80 sentences we recorded from the speakers, trained a Gaussian mixture model based on 13-dimensional MFCCs, and then we tested that model with the low and the mid and the high-pitched vowels, the fall and fall rise and rise, and we're mostly interested in, do we get a significant difference between the steady state and the contour vowels? And that was the case in that here, where you can see, though, that the mid and the fall rise, they are maybe pretty close, but we see that the fall and the rise were also offered more richer information for our recognition system to better recognize the vowels under these contour conditions. And then we did the same with humans. So we had only 4 voices in here, 4 female voices that worked best for the computers. We did the same in humans. Oh, there is Peter French joining the audience. I see, Peter, I talked about your company before, actually, that you missed it. But in any case, so we had humans do it. It's impossible for a small experiment to train humans on 15 voices. So we reduced it to 4 voices that worked well in the computer experiment, and we trained them. We trained listeners until they had 75% correct. Then they went into a test with only the vowels, and there we see an even stronger magnitude of difference between the steady state and the contour vowels. So basically, for the human listeners, the contour vowels was helped a lot for recognizing speakers under those conditions. So as an interim conclusion, we can maybe state that, well, sweeping harmonics, they maximize the voice identity, which would basically then be an argument for voice identity is dynamic. We can either sweep on a vowel, increase the identity of the vowel, or we can speak in a steady state way on vowels, have less sweeping, and should have less maxima. Should lower our recognition probability with that. So that's in line with previous ideas. Maximizing variability maximizes the recognition performance. That is something that other people found in face research as well. There is research by Mike Burton, for example, from York, arguing that knowledge about within speaker variability helps to identify faces. That's quite plausible when you think like, oh, if you only see the face from the front, you will probably never learn it the way as when you see it from all sorts of different perspectives, see it moving and get a lot of variability from that face. And that's basically where that idea also about the sweeping harmonics leads us to. And in voice research, actually, Nadine Levan has introduced that as the idea of saying, well, the variability itself is probably the signal of individuality. Yeah, so all these different variability we get over time. So to understand individuality, we really need to understand that variability instead of reducing it to a single figure for a speaker. So now the next question would basically be, do speakers control indexicality with speaking? Is that something that might occur somewhere in speech situations? Are there maybe certain speaking styles in which speakers speak with more or less sweeping? And would these speaking styles then lead to a better recognition, would maximize the recognition probability of speakers? And for this, let's have a look at a speaking style that probably many of you know. I'm going to play you the example here. It's from an American English example.
You have blocks on your shirts.
Yeah, okay. So what you heard here is a speaking style that we typically refer to as infant-directed speech, as a mother addressing her infant, and that speaking style is characterized by a lot of sweeping. And in the past, people have often asked how are the acoustic characteristics of infant-directed styles motivated? Why are people using, for example, these amounts of sweeping? There were early approaches where people looked at whether that might enhance the intelligibility of vowels, the acquisition of vowel systems, that you get more variability from the vowels, that the vowels space actually expands to a larger space, and that would help learning the vowel space better. But there's a lot of confounding results from that, and many studies that showed, well, really there's too much variability in there, and for learning purposes, learning the vowel system, for example, this is not really well suited. And you can also imagine, well, when you learn another language, or you teach another language, maybe some of you are language teachers, you wouldn't go ahead and teach with a very small sweeping variability your language. So that's not really plausible to do anything like that. So the question is, why is that sweeping there? And you can probably, connecting to the previous topic, my argument would be, well, we're sweeping here to increase the recognizability, because we want the baby to recognize the mother. And that was a hypothesis that we started testing actually a few years ago, and are still testing, because it's turned out that it's quite complex to get convincing results on it. But the hypothesis would be, oh, sorry, there's an E missing here in the voice. Hypothesis would be that voice recognition increases when acquired from infant-directed speech, possibly due to this large amount of sweeping. Now, then we know, though, that variable speaking styles, when we have little familiarization with the speaker, that variable speaking styles are problematic. So if you only hear a few sentences by a speaker and you have to recognize that speaker afterwards, if you hear that in infant-directed speech, and sometimes the person speaks high and low and fast and slow, then probably that within speaker variability is so strong that it would initially give you a very low recognition performance. And the typical adult-directed speech that is much more static. So the way I'm speaking now would probably give us a much faster increase in recognition performance with the amount of training data. But our hypothesis is that, well, at some point in time, basically with the amount of training data increasing, then at some point infant-directed speech takes over, because infant-directed speech gives us then a more comprehensive model of the speaker with all the possible speaker variability, voice speaker variability that is available in the voice. So we're basically serving the infant on a tablet. Here, this is my voice under all sorts of different facets, and take this, learn it from here, and you can recognize me under any situation at a later stage. So if we are thinking about, well, inducing an infant over several months with infant-directed speech, that we probably might get to, or we should get to that point that the infant-directed speech then takes over. Well, we tested this hypothesis first with machine learning, using infant-directed and adult-directed speech from 3 languages: US English, Swiss German, and Hungarian, trying to maximize the diversity a little bit. It's quite difficult to find appropriate data for that, because we need utterances from the same speaker produced in adult and infant-directed speech. Ideally, comparable utterances, ideally maybe the same sentences for some of the models we're using, and that is not readily available. But for these 3 languages, we got hold of a bunch of speakers. The Swiss German ones we actually recorded here in our lab together with a colleague Moritz down from psychology here. And all the speakers read about 20 utterances in each style, and we modeled them with 13-dimensional MFCCs for the recognition, and used the Gaussian mixture model. I'm not talking about all the details now about the different models and the acoustic modeling that we used and why the choices, but the choices for that particular model was that we thought, well, the Gaussian mixture model is probably closest to human timbre perception, and it's probably closest to a stage at which the infant really relies very little on any language information in the signal, but heavily on the acoustic impression that it gets from the voices. But if you're interested, of course, we can talk about that in the discussion. We had a training test split of 70-30 and a 20-fold replication, and for the test conditions, we trained the model with adult-directed speech and wanted to see how it performs on infant-directed speech, and we trained it on infant-directed speech and wanted to see then how it performs on adult-directed speech. We didn't particularly look at the ADS and IDS conditions. Sorry, I just lacked the word for the, but where we keep the speaking style the same, and we didn't look at this one because obviously the performance of the model is much better for this. As the results, basically for US English, Hungarian, and Swiss German, we saw that the orange line is the training in IDS, testing in ADS, and the turquoise line is the training in ADS, testing in IDS. And we saw that in the beginning, sometimes with the US English, I mean, the performances are much lower. This is why they are much closer together. But with US English, we even saw, and at some points with Swiss German as well, that in the beginning, the infant-directed speech was below the adult-directed speech training line. So we basically get something similar to what is exaggerated here in that hypothesis that I showed you before. But then very quickly, the infant-directed speech took over with the amount of training data that we gave. So at a certain percentage of training data that is totally relative for the different setups that we have here, but from a certain percentage of training data, then the infant-directed training actually was of an advantage, and also stayed an advantage over the whole data sets that we had until the end. So learning from a high variability style and recognizing in a low variability ultimately leads to better performance compared to learning from a low variability and generalizing to a high variability style. That shouldn't be so surprising in particular for these models. And then we wanted to know, can we also generalize from infant-directed speech to other more high variability styles? And would we what would be the performance for this? So for the Swiss German speakers, we actually had also a picture description and a storytelling free speech task, and we used the infant directed and the adult, sorry, I only said infant directed for training the same models as before, but also the adult directed models, of course. So we had the IDS and the ADS models that we trained before and used it on the picture description and the storytelling task. And we also saw that then the thick black line is the adult directed training, and the brighter line is the infant directed training. And we saw that the infant directed training was with certain amount of training data kept constantly above the adult directed training, also then generalizing to different types of variability. And then also interesting, we compared it to another speaking style that is also often how should I say, also often referred to as being characterized by higher variability, in particular in intonation, and that speaking style is referred to as clear speech. But clear speech obviously is clearly targeted at individuality and not at recognizing a speaker. So we would actually hypothesize, well, with clear speech, then training a model with clear speech, that should perform poorer on recognizing speakers because the model doesn't know so much about the speaker variability. And that was the case here. The blue line is a model trained with ADS, or in this case as with clear speech, we would typically refer to it as conversational speech. So a model trained with conversational speech and tested with clear speech. And the red line is the one trained with clear speech and tested with conversational speech. And we found where this model, we had more data and a total. And so at some point they saturated and both lines came together. But over a long period of training data, actually the model that was trained with conversational speech worked better. We found in the end that, well, yes, there is more intonation variability maybe in clear speech, but when it gets to the vowels in clear speech, we typically use less sweeping, but more pronounced steady state vocalic parts, because we wouldn't talk to someone who is hard of hearing or doesn't understand. We would say, like, this is a table here in front of me. Yeah, so we would make those vowels very pronounced, even though the overall intonation might vary a bit, but we wouldn't say like, this is a table here in front of it, introducing a lot of sweeping. Yeah, so we are probably dealing with two different types of pitch variability here, and this makes us think more and more, well, the one maybe serves speaker recognition more and the other one serves intelligibility. Okay, so the interpretation from this is that the acoustics of IDS maximizes speaker-specific detail compared to styles that are targeted at intelligibility, and we argue that IDS is a style that maximizes speaker-specific properties and is therefore best suited for acquiring voice identity. And that's an important factor in identity maximization, is most likely that sweeping. There is a part of that story is in the preprint. If you want to read it, it's not the recognition over time. It's basically all the results that we had on this, but the full paper on this should be out very soon. Now, the $1 million question on this is obviously now, well, this was a Gaussian mixture model. How much does that tell us? So does that actually hold for humans? And training and testing humans over time with infant-directed speech is quite a bit of a task. And so far we haven't been. I don't know why this always happens with my thumb up there in the picture, but yeah. So far we haven't been successful with that. It also needs a lot of infant-directed speech that is currently we are in the process of recording. And then the $1 billion question after that probably is that, well, is this coincidence or is it an evolutionary mechanism? Did IDS maybe evolve as a special speaking style to foster mother-child bonding through robust familiarization with the mother's voice? So is that something that was wanted in the end by evolution, or is that something that just happened as a coincidental byproduct, which is perfectly possible, I think. So we have started testing with infants now with a colleague Rushin Shi from Montreal and Elisa Pellegrino here, and we have a PhD student, Alexandra Metzger, and here now is setting up infant experiments. Rushin has already tested that in Montreal with non-speakers of Swiss German. Now we want the native speakers and running experiments that tell us more whether infant-directed styles actually are advantageous for children, for infants to acquire the mothers. But yeah, so we looked at situations where voices are relevant for interpreting communication and structuring communication in the beginning. And but I think that there is a much deeper integration actually of voice recognition in speech communication, in particular, as the title says, in speech communication with language. And that is that voices are essentially or essential to process language in dialogue. So if I play you a dialogue, this particular dialogue here, and I'm not going to do the experiment because it takes a long time. But what I want you to do is basically, so I'm not waiting for your feedback. I mean that what I want you to do is to figure out who cannot be bothered about phonetics and phonology talk, and who will be joining for dinner tonight. And I play you the first sample.
Yes, I am. Are you not here?
No, I thought this talk on voice recognition was pretty dull, so I could not be bothered.
Oh, I see. That's a pity.
In any case, I'll be joining the crowd for dinner tonight, and I'll see you and everybody else there.
Okay, so probably if you paid attention to the voices, there was a male and a female. The female is Katie, the male is Mike. And then Mike said in the end, oh, yes, I'll be joining the crowd for dinner tonight, and I see everyone there. So he's the one joining for dinner. And he said before, oh, no, I thought this talk on voice recognition looks pretty dull. I could not be bothered. So he was the one who didn't want to see the talk. So Katie was there. Mike was not there. Now I play you the dialogue again. Pay attention to the voices, pay attention to the outcome.
Yeah, I thought this talk on voice was dull, so I could not be bothered.
Oh, I see. That's a pity. In any case, I'll be joining the crowd for dinner tonight, and I'll see you and everybody else there.
Yeah, so now the lines about now I thought this talk on voice recognition was pretty dull was taken on by Katie, and the last line, in any case, I'll be joining the crowd for dinner tonight, was taken by Mike. So in this case, it's Katie who didn't want to come to the conference and listen to the talk, and it was Mike who will be coming for dinner. Yeah, so that's a different outcome. If we really want to know about the outcome of the dialogue, which we should when we listen to the dialogue, it's the essential information here. So also in terms of linguistically, then we have to be able to distinguish the voices actually to get the cues. We have to be able to recognize recognize the voices to get the respective cues to actually analyze that particular dialogue. And I would say that is something that is occurring in everyday life constantly. Yeah, so we're constantly in dialogue in communications where we interpret the outcome of that communication based on voice recognition process. And that's what I mean. That's why voice recognition is essentially integrated into that dialogue processing. And what you need to do for this is, like right in the beginning, I introduced you to this discrimination and identification difference, and this comes back here again. So what you need to do in the first place, you hear the first sentence, you hear the second, or so you hear the first utterance, you hear the second utterance, and the first thing is probably that you have to do is a discrimination of unfamiliar voices. Yeah, so you're not familiar with these voices. You in the second example, you have to conclude, oh, now someone else is speaking, actually to attribute that to a different person. But then in the third utterance, you already have to do an identification. So identification basically means you need to have a model of Katie who was producing the first utterance. You already need to have a model for identification and recognizing that person. And I would call that process then identification of a just familiar voice as opposed to identification of a familiar voice, because obviously the only thing we know about that voice is, oh, that's the person who spoke first, but we don't know anything else. But that is enough as an attribute maybe for that would allow identification. So you can see that is a situation where identification emerges then from a micro situation, identification and that when model building for those particular speakers start. So that's the general idea here. It's about integration of linguistic and voice identity processing. It has certain implications for the production and the perception. For the production, the implication is, well, it needs to be clear very early during a turn who is actually speaking. So the turns should basically be designed in a way as that the speaker-specific information is at the beginning, because we need to conclude right at the beginning of a turn who is taking it on. So to maximize the speaker identity, markers towards the beginning of the turn or the end of the turn, also that we can contrast it nicely with the next turn. And in perception, the implication for perception would be that attention to voice identity needs to be high at the beginning of the turns or at the turn boundary. So when the prosodic signs basically lead to the end of the turn of one speaker, probably our perception mechanisms, our attention mechanisms that we talked about in the beginning that are open for speaker recognition, for voice recognition, they kick in at that point and say that, okay, now I need to be aware who is actually talking next, and then conclude as fast as possible who is talking next to then focus actually what is that person saying. Okay. So the question is, do listeners pay more attention to voices at the beginning of the turn? And yeah, maybe I'm jumping over that slide. That's an example about the attention, but just to conclude this, just telling you we have two large projects in which we are looking at these phenomena. One is the so-called, or is a project in the so-called VOX network, Voice Communication Sciences Network. That's a network funded by the European Union, where around 20 partners are in with, it's a PhD doctorate school where 20 partners are in with around 20 PhD students, and we have 2 PhD students here in Zurich in that network, with which we are looking at all sorts of different aspects in voice communication sciences. And one of the projects is on the time course of identity perception that I'm doing together with Pascal Bellin in Marseille, who is also the head of that network. And we have that topic also in another project, a network project here in Switzerland, Evolving Language. It's a so-called National Center of Competence in Research, and there I have a project on the neural integration of identity and conversation together with Alexi Ave Adelman in Geneva, and there we're planning to we are right now in the execution stage of an MEG experiment in which we want to see how the brain changes attention during the perception of different turns in dialogues. So where did I take you in this talk? Well, basically, I wanted to show you that voice identity information is dynamic rather than static, that speakers can control or modulate that information, for example, by maximizing vocal tract information through sweeping in speaking styles, for example, and that Listeners rely on identity information to process linguistic information, for example, in dialogues, but in many other communication situations. And voice recognition is therefore an integrated part of linguistic processing as well. And finally, basically, my hope, my message came across that understanding how voice recognition is integrated into communication offers a huge opportunity, offers huge opportunities to understand the functions, evolution, and development of voice recognition abilities. And with this, yes, I want to conclude then, and thank you for being here. Thank you for listening, and happy to discuss with you anything.